Hello, everyone. Welcome to the Carolina Weather Group. We're happy to have you this evening. And tonight we're happy to have Dr. Cameron Homeyer. He is the associate professor at the University of Oklahoma. We're going to be talking about some research that he's doing in the troposphere and talking about a couple of new projects that are going on. In fact, one that I did not know about until earlier today, and that is the dynamics and chemistry of summer stratosphere, the field campaign, which I'm really interested to find out about. We're going to talk about some thunderstorms and how we can detect those and better forecast those. So, Cameron, we welcome you to the program. And our first question to every guest is, how did you kind of get caught up into this weather bug that we all have? What is like your weather story that kind of got you hooked into this?
Yeah, well, so I grew up in Texas and Louisiana in my early life, and we experienced a lot of tropical cyclones, landfalling tropical cyclones. Biggest impactful event that I remember growing up was Tropical Storm Allison, and at my house it dropped over 19 inches of rain in just over 24 hours. I've been an avid gardener my whole life. It kind of runs in the family, farming and gardening. And I had this beautiful garden, best garden I ever had. And then Tropical Storm Allison came and just ruined it. And so I remember being very, very frustrated at that whenever I was younger. So I had that. We had, ice storms. We had just about everything in Southeast Texas, where I spent most of my early years. And because I was interested in gardening, farming, sort of agricultural things, and it impacted directly by the weather, I sunk a lot of my time into looking at radar data and forecasts, and really trying to get a handle on it whenever I was in middle school and high school. And by the time I was coming up to graduate high school, I was, a little over an hour away from Texas A&M University, and they had a meteorology program. And I thought, well, I'd like to go there. And so I applied there. The only school I applied to for college. I wasn't sure if I was going to get in. My backup plan was to go to culinary school in Houston, because they had a great culinary school there. And I also really like to cook. So I thought, if I can't get into meteorology, I'll go to culinary school. And it all worked out. Got into meteorology, went to Texas A&M. Ended up staying there for all 3 degrees, all the way through graduate school, and then left there and went to Colorado for a couple of years before I came to Oklahoma.
When you went to Colorado, was that collegiate related, or have you always been in the collegiate path, or did you do any National Weather Service or broadcast? Or
yeah, I went to the National Center for Atmospheric Research there and did a postdoc. So after I finished my PhD, spent 2 years there doing some independent research before I, felt the draw to go back to academia. I found that I missed, being in academia, working with students, and I wanted to go back and be a faculty member. So I applied to, a dozen jobs or so, and ended up, choosing Oklahoma.
I want to start with radars, and I know we have some different topics we want to talk about, but you have helped come up with the grid rad, and we'll talk a little bit about that. But first of all, I want to kind of get the 30,000 foot scape. We've talked about radars on this program before, so I don't want to kind of get into the details of how they work, but I want to get your perspective on the overall radar coverage and how we are as the United States. How are we doing with radar coverage? We continue to see over storm coverages. In fact, a couple of weeks ago in Arkansas, where there was a tornado emergency issued for Jonesboro area, and it was kind of in this radar hole. And so we're kind of pulling radar from a lot of different locations, trying to get a better look at the storm. So how do you think we are right now as a country with our radar coverage?
Well, the United States is the most advanced country in the world in terms of atmospheric observing, and radar is no different than a lot of the other platforms that we have. I'd say 30,000 foot view, we have this incredible network of radars in the United States that have been maintained for over 2 decades and have provided a wealth of observations. Those observations aren't just excellent for warning and life-saving measures that we commonly pore over, for, but also for research. And when it comes to my involvement in radar a lot, it's recognizing the fact that we have this long-standing network that's available to be leveraged for a lot of climatological studies of storms, and it's a largely untapped resource. In terms of holes, people usually talk about radar holes because they're focused on the low-level coverage, the lowest few kilometers above ground, and there you have to be within 80, 90 kilometers of a radar location to get really good low-level coverage. Once you get past 100 kilometers away, it's difficult to see because the curvature of the Earth is going down and the radar beam is going up, and you really start to get that quick separation between where the lowest observation is and the ground. And so when we talk about holes, we usually talk about those and that low-level coverage in particular, because if you look at the full three-dimensional coverage, we actually have complete coverage of the entire United States. We can see any really deep things like thunderstorms anywhere. The problem is, from a warning perspective, we really want to know about low-level rotation and its evolution, and what it says about potential for tornado genesis and those kind of impacts. And that's where that becomes a problem. We have a few places where I think adding radars would be really, really helpful. Northeast Texas and Central Texas, East Central Texas are one real important corridor where we can make a big impact by improving coverage there, because we've got a lot of dense population in that region. You mentioned Arkansas. Northern Arkansas is another location that could benefit from that. The Southeast, really the Eastern US, east of the plains, is the densest area of the entire network, especially the Southeast. And we've got really excellent coverage in that region. When you get to the high plains is where you have some of the more pervasive coverage gaps that aren't really restricted by sighting issues. And when I say sighting issues, you go out west in the mountains, it's really difficult to find a great location where you can place a radar and not just stare at a mountain the entire time when you're trying to take an observation. So when you get into the northern plains, we've got a lot of big storms up, really north of Kansas, things really start to degrade in terms of coverage. In that region, we could really benefit from more radars. The motivation is not as strong there because the population density is much lower. And it's really a balance from a national level of supporting the most individuals that we have to support and providing comprehensive coverage. And that's where, historically they've made some sacrifices.
I think that's a good segue into what I want to ask you about, which is your research, because I know your research focuses on that upper level of the atmosphere, of the troposphere, and especially the tropopause. So is there a way that the radar from a distance looking at the upper levels can help you with your research, and how else do you measure that?
In terms of my group's work on severe storms in particular, which is often a high impact event that you would really be focused on in terms of radar observations, our focus in the past 5 to 10 years on that has been trying to figure out what characteristics of the storm at upper levels may be most useful to identifying storms that maybe have a higher propensity for tornadoes or hail or winds. When it comes to hail upper level observations are really excellent and key. I mean, that's how we do a lot of radar-based climatologies of hail. It's all the upper level observations. It's not so much what's happening down near the surface. And when it comes to tornadoes, that's almost a completely different problem. It's all about what's happening down low, but you need sufficient support from the storm above to ultimately generate a tornado, right? There's plenty of rotation in a lot of environments, but it's about that rotation being stretched by an updraft to form a tornado. And if you can look at the upper levels of the storms, you can identify strong updrafts, strong storms that are able to provide that support to form tornadoes below. But it's not, neither of these things are sufficient. they're helpful, but they're insufficient. You really need a complete picture to get the best knowledge. In terms of my group's research on that problem, what we found is that we focus a lot on storms that reach above the tropopause, right? So a lot of people, when they think about the atmosphere, they think about the weather. Once you get to the tropopause, people tend to not pay a whole lot of attention beyond that point, because the tropopause is right at the top of the layer that we live in, and where most of all the storm activity is confined to. But when storms are really strong, they can reach above the tropopause into the stratosphere. And my group is interested in all the things that happen to the stratosphere as well. But the storms that do that also happen to be the storms that produce the vast majority of severe weather. And certain types of those storms, combination of radar and satellite information, we can identify some of the most severe storms by looking at the storm tops. But getting into really specific hazard type communication and warning decision making, that also depends crucially on the low level data.
Well, let's talk about that. You overshooting tops, I know, is a big thing that you like studying, and that kind of relates with what we're talking about. So talk a little bit about the importance of those for who may not be as weather savvy as others, and then kind of what you guys are doing with that.
An overshooting top itself is just a protrusion of a cloud dome in a thunderstorm that reaches above the broader anvil cloud. So if you look at a thunderstorm, we call it an anvil cloud because it looks like an old metal anvil. The top of the thunderstorm usually spreads out really rapidly in the upper troposphere just beneath the tropopause. But within the core of the storm, a really strong upward motion in the core of the storm, the rising air in that region usually has so much speed by the time it reaches the tropopause that it reaches even higher. And that level that it reaches, if it also happens to coincide with the tropopause, reaches into the stratosphere, which is most of what I focus on in terms of overshooting convection. We call it tropopause overshooting convection, to be really specific. Yeah, that has a lot of really relevant impacts to climate, because if you have storms reaching up into the stratosphere, they put water there, water vapor there, and water vapor is a really powerful greenhouse gas, and that can help modify climate. And we have suggestions from climate models that support for these types of storms is increasing over time. As the globe is warming, we have environments that are more conducive to thunderstorms. Maybe not severe thunderstorms, but more conducive to thunderstorms, and that can lead to greater impacts on the stratosphere, which is what that field campaign is all about. We're trying to chase air that's coming out of overshooting tops in the stratosphere and measure that with a whole bunch of instruments on an aircraft. And that helps us to really understand what the impacts are to climate. And we can leverage some of that information to try to understand what that says about the broader characteristics of the storm, maybe even looking at something like its severity.
What are you looking for when you just don't send an airplane up, I'm assuming, every day? Like, tell us the logistics of that and how everything goes along with that, and kind of just what specifically you guys are looking for, and then what you do with that data once you get it.
Well, we are sending an airplane up just about every day, every other day, but only for a confined period. So we had our first deployment. This is a NASA field project. So it's the Earth Ventures suborbital campaign. It's one of these $30 million field projects that NASA funds every 5 years. And this campaign, we have the NASA ER2. The ER2 is very similar to a U2, which is a very well-known spy plane. Right? It flies very, very high in the atmosphere. In fact, we reach up 60,000 feet with this aircraft on the regular. Almost every flight we can get that high. And what we're trying to do is identify storms that reach above the tropopause with radar data in the United States and with satellite observations from GOES. And we look for these overshooting tops, and then we track them with a trajectory model. It's a really rigorous, complicated process to do all these things. We combine all the radar data from all the radars into one big unified product, and then we look for storms that reach above the tropopause, and then we put in what we call particles, basically, little parcels of air that we then move with the atmospheric winds based on the forecast models, and predict where all the air from these overshoots is going. And then we plan a flight and take off with the airplane and go and sample where we expect that material to be. And most of the time, we see exactly what we're looking for. And that's a whole lot of enhanced water vapor in the stratosphere, but it can include other things like tropospheric gases that are coming out of pollution from man-made, from human activity. So we burn a lot of fossil fuels. We burn a lot of fuels for energy and for our cars and all these things. There's a lot of really unique gases that come out of that that are in the troposphere, and not very much of that in the stratosphere. And so we can look at the transport of air, and we can look at the amount of water that's impacted in the stratosphere, and understand what these storms are doing to stratospheric composition.
I want to go back to a little bit about radar, because we didn't really get into what you've been working on, and that's something called GridRad. So could you tell us a little bit about this? It looks really like a really cool product. Again, not familiar with it until discussing things with you off the air. So tell us a little bit about that, and what the push was for.
Yeah, well, the push was trying to identify overshooting tops. That was the goal. And there are a few other alternative data sets that are really similar to this out there in the community. I mean, some products out of NOAA and these sorts of things, those groups. But the essence of this product is we take all the operational radars and we blend them into one unified, multi-radar data set. And we have several different public versions of this GridRad data out there that have different span in terms of how broad they reach across the United States, and what really they're made to understand best. But ultimately, it formed out of our focus on wanting to get really good estimates and climatological evaluation of the occurrence of tropopause overshooting storms. And so we built these products. We made a whole bunch of the multi-radar products every hour for over 20 years. The first time that we did this, we did it for everything kind of east of the Rockies in the United States, and we made the first detailed radar-based climatology of tropopause overshooting convection in the United States, and that is complements a lot of what before was mainly done from satellite. So now we've been doing this with the ground-based radars. We use a very unique set of methods to build the data, which is very different than the approach in some other groups, because our primary motivation is getting tropopause overshooting convection. We've created the algorithms to try to get the vertical structure of the storm as best as we can. We've validated it against other external data sets. Whereas a lot of the focus on operational NOAA side for making these types of products is precipitation estimates. They want really, really good precipitation estimates so that they can have good decision making for flash flooding events, and all these sorts of watershed analyses that are super, super important, and big impacts. But they have ties to the FAA. They use some of those products because it gives them a unified product to look at how tall storms are, and they do severe storms research with the blended products from the other groups as well as we do with ours. But our methods and our data set was motivated by trying to understand tropopause overshooting convection better.
We'll switch gears a little bit here now and go into some fun questions that we like to ask all of our guests. And I've been looking forward to this ever since you said that you were considering culinary school out of college. If you weren't going to be a meteorologist, you might have been a chef. So this is that's great, because I'm always asking about what the best place to eat in a town is. And since I visited Norman, I know a couple spots, but I want to hear your opinion. If you're coming to Norman, to visit for a conference, workshop, whatever, like I did once, are you, what is one or more restaurants that you got to go visit?
My wife and I like to go to Legends every once in a while. Legends has been here forever, and it's down right in the heart of Norman, not too far from campus. And they're known for these incredible desserts, but and they used to have this really great salad bar. I think post-COVID they don't have the open salad bar anymore. But they have, the full menu is very good, but I think the desserts are really unique, and that all around is a great dinner place. There's a number of places that are really good for different occasions and different settings. We also really like Benvenuti's, which is about the nicest restaurant that we have here in Norman. And it's across the street a bit from another good restaurant in downtown called Scratch. So those are a few good places. For me, I'm a big breakfast guy. I love breakfast, and my favorite breakfast place in Norman is Juan del Fuego, which is like a Mexi diner type place. It's really really good Mexican themed breakfast, and there's another one similar to that that's newer. It's also good, called El Huevo. But yeah, Juan del Fuego's one of my favorite breakfast places. We have a chain of breakfast restaurants here. It's a local chain in a few different places up in Oklahoma City and Norman called Neighborhood Jam, which is also a very good breakfast place. That's right down on Main Street. But breakfast options, I mean, they just keep getting better in Norman, which is perfect for me, because it's usually what I eat out the most is breakfast. Dinners are less common.
I have to jump in on this because I ate at a place called Honey Bunny Biscuit Company in Oklahoma City. Have you guys been there yet?
Yeah, I've been there.
Yeah, love that place. It's a great place. So you'll have to check that out, Andrew.
What is something that a visitor to Central Oklahoma ought to do when they're coming to town, when they have some spare time?
If you're coming to Norman in particular, go to the Sam Noble Museum. Okay, that it's a real treasure. I'm not sure Norman deserves to have that museum, because I mean, it's not what you would think of when you think of Norman. It's just a really unique thing to have. It's got a lot of really incredible and unique fossils in there. It's the largest skull of any land mammal ever found. This big Pentaceratops is in there, and it's over 7 feet tall. You stand in front of that thing, and it's just awe-inspiring. And just this really great dinosaur exhibit, and then they've got a really great Native American exhibit upstairs. It's all different tribes of Oklahoma, which is really neat. I have 5 kids, so I usually like to go to the museums and these sorts of things a lot, and they really love, especially my 3-year-old boy, really love Sam Noble Museum. But broadly, just an environmental type situation. I mean, if you come to Central Oklahoma, right time of year, you might as well storm chase. I mean, there's you don't have to do much. It's not too hard to chase storms, and there's always beautiful skyscapes to look at. Not that the University of Oklahoma condones storm chasing. I always emphasize that this is not a university related activity, but just outside of that, as a visitor to Oklahoma, if you do it well and safely, that's a good fun thing to do. But we also have some good hiking places not too far away. The Wichita Mountains, just a little over an hour away from Norman, and Mount Scott, one mountain kind of out here in the plains that doesn't really belong. It's an interesting place, but it's nice. A lot of great hiking out west of the mountain, and actually good hiking out by Lake Thunderbird, which is not the nicest lake in the world, but it's really great trees and hiking trails all around the lake, the southern end of the lake. So I like to go out there and do that. I like to fish a lot. Kids and I will go fish just about any body of water around here, and good fishing and good good outdoors activities.
All right, one of my favorite parts about your class that I took last year was at the end of every class, you'd tell us a dad joke. So, putting you on the spot, what's one of your favorites?
Do you know what Yoda's last name is?
I don't.
Leahy-hoo. Yeah, Leahy-hoo. Yeah, like Yoda Leahy-hoo.
Oh, I had to think about that one.
I like that one a lot.
That's a good one. That's a good one.
I probably didn't tell that one to class. I
don't remember that one.
Wait, what do you call a dog that loves magic? A labracadabrador. I like that one. That's another one of my favorites.
Since if meteorology didn't work out, it was going to be the culinary arts. So, I mean, what's your favorite meal to prepare? I mean, if you like cooking, we got to know your favorite meal to prepare.
In terms of my favorite meal to prepare, it's usually a good steak. My favorite steak is probably a dry aged ribeye, at least inch thick. But you know, good filet mignon, good prime filet mignon is also a great option. But I really prefer steak. It's a more than a day long process for me. I dry brine it, which means, you just put a good amount of kosher salt on it, stick it on a cooling rack in your fridge overnight. Meat draws all that salt in, so it's really well seasoned. I'll put a little garlic powder and black pepper on there, and then I'll grill it to the temperature it's supposed to be cooked, which is 135 degrees, medium rare. Not supposed to be made any other way. And then I'll usually pair it with I don't know, a wide range of sides. One of my favorite sides to make is roasted Brussels sprouts. And so I'll roast Brussels sprouts with a good amount of minced garlic, bacon, lots of good stuff in there, salt, pepper, of course. And then I'll drizzle a balsamic reduction on them once they come out of the oven. So about 30 minutes in the oven, bring them out, balsamic reduction. And then potatoes are a good bet. Otherwise, it's always good, good mashed potato or a baked potato, or even, if you get those little fingerling potatoes, really small ones, and season them up and roast them, those are good.
All right, that's it. I'm on my way over to Dr. Homeyer's house for dinner tomorrow night.
Yeah, we're on our way. You go ahead and start that steak prep right now. Well, Dr. Homeyer, we appreciate your time tonight. If our audience wants to follow any of your work, you have a Twitter page or maybe a website or something like that they can follow?
Yeah, I mean, you could Google my name. I think I'm the only Cameron Homeyer in the world, but you'll probably find either connections to the school meteorology webpage at OU. I've got a pretty detailed group webpage up there. You can look at real-time overshooting products. We build these for the field project. Right now, you can go on and look at a loop of the radar observations or the satellite observations and what the overshoots look like. And the satellite, all those products, that's all coming from that colleague and group from NASA Langley, Chris Bedka and his group. And then, all of our radar products up there. I'm on Twitter. I usually post a lot of science related things on there, rarely personal things, but if it is personal, it's usually food. If I'm cooking something. I like to rotisserie a chicken every once in a while, and I'll usually say, the vortical bird has returned. It's horizontal vorticity on the grill. But I'm on Twitter at @MostScientist. Also, search my name on there, probably find me that way too. But yeah, I'm happy to interact with folks, and drop me a line or ask me questions on Twitter. Happy to weigh in.
Well, we appreciate your time, and thank you for joining us. And thank you all for watching us here at the Carolina Weather Group and listening to us. Please be sure to like and subscribe to the YouTube page and to your favorite podcast so you can get up to the minute latest information when we release new podcasts or when we go do severe weather coverage. So for everyone here, we thank you for watching. We'll see you back here real soon.